Imagine two of humanity's most powerful tools for exploring the unknown. On one side, the Google Quantum Lab, a place where the boundaries of computation are being pushed further than ever before. And on the other, the James Webb Space Telescope, our most advanced eye in the sky, peering deeper into the universe than any telescope before it. The Quantum Lab doesn't rely on traditional lenses or mirrors. Instead, it harnesses the strange and powerful laws of quantum mechanics, the science of the unimaginably small, to perform calculations that would take even the fastest supercomputers thousands of years. These quantum computers allow us to ask the universe questions in its own language: atoms, particles, probability, and uncertainty. They open doors to new realms of possibility, letting us simulate molecules, crack codes, and even explore the origins of matter itself. Meanwhile, the James Webb Space Telescope is the sharpest, most sensitive eye we've ever built, floating a million miles from Earth, capturing the faintest, oldest light in the cosmos, light that has traveled for billions of years to reach us. Webb peers back in time, seeing galaxies as they were in the earliest days of the universe, revealing the vastness and complexity of our cosmic stage and helping us understand how stars and planets first formed. One tool looks inward, probing the fundamental rules of reality, searching for the building blocks of everything we know. The other looks outward, at the grandest structures in the universe, mapping the architecture of galaxies and the mysteries of dark matter and energy. They operate in different realms, one buried deep in a high-security lab surrounded by cutting-edge technology and brilliant minds, the other drifting in the silent, endless expanse of space, far beyond the reach of our planet's atmosphere. At first glance, you wouldn't expect their paths to cross. Their missions seem worlds apart. But science thrives on unexpected connections, on the moments when different fields collide and spark new ideas. Sometimes, the most profound discoveries happen when we link seemingly unrelated fields and let curiosity guide us into uncharted territory. What if these two quests, the quantum and the cosmic, stumbled upon the same mystery, a puzzle that bridges the smallest and largest scales of existence? What if both the Quantum Lab and the Webb Telescope caught a glimpse of something extraordinary, something hidden in plain sight, waiting to be discovered? This is the heart of a recent electrifying claim, a story where the quantum and the cosmic might just intersect, changing our understanding of reality itself. We live in a world defined by three familiar dimensions: length, width, and height. These are the directions we move in, the axes that shape our reality, and the framework for everything we see and touch. But what if there's another direction, one that exists beyond our senses? A hidden path woven into the fabric of the universe, invisible to us but just as real. Imagine a creature living on a flat sheet of paper. Its entire universe is two-dimensional. It can move forward, backward, left and right, but nothing else. The concept of up or down is completely alien to it, something it can't even imagine. If a three-dimensional object, like a sphere, passes through its world, the creature only sees a slice, a circle that appears, changes size, and then vanishes without explanation. An invisible dimension could be like that, a direction so small, so tightly curled up, that we never notice it, even though it's all around us. Think of a garden hose. From far away, it looks like a simple line, but as you get closer, you see its roundness, its hidden dimension wrapped around itself. Our universe might have extra dimensions, tightly curled up at every point in space, hidden from our senses but influencing the way particles move and interact. We could be moving through these dimensions constantly, looping back on ourselves in ways we can't perceive. Our paths shaped by spaces we can't see. Or maybe we're stuck in our three dimensions, like a character trapped on a movie screen, while a much larger reality surrounds us just out of reach. In this scenario, our universe is a three-dimensional brain floating in a higher dimensional bulk, a vast space with more directions than we can imagine. Other dimensions exist all around us, but we, and most forces we know, are confined to our brain, unable to escape into the higher dimensional space. It's like being a part of a movie, unable to step off the screen, forever bound to our limited world. We're part of a much larger reality, but we can't escape our designated space, no matter how hard we try. The idea of invisible dimensions isn't just science fiction. It's a real possibility in modern physics, explored by scientists searching for the universe's deepest secrets. And now, with new experiments and powerful telescopes, there may be evidence that these hidden dimensions are more than just theory. They could be a fundamental part of reality itself. The story begins in two places: the Google Quantum Lab and the James Webb Space Telescope. At Google, scientists use their quantum computer Sycamore to simulate a wormhole, a theoretical tunnel through space-time. During the simulation, a single quantum bit seemed to leak out, vanishing and reappearing in a way that defied known physics. Meanwhile, astronomers using Webb studied gravitational lensing around the galaxy cluster Abell 2744. They noticed light bending more than Einstein's theory predicted. An unexplained gravitational effect. A junior astrophysicist saw a connection. The energy signature of the quantum leak matched the missing gravitational energy in the Webb data. The wild hypothesis: what if gravity can leak into an extra dimension? And both experiments detected the same phenomenon. Two different tools, one mysterious signal. Picture our universe as a giant trampoline. Imagine this trampoline as representing our three familiar dimensions, stretching out in every direction. Now place a heavy bowling ball right in the center. The trampoline curves downward, creating a dip, just like how a massive object, such as a planet or a star, warps the fabric of space-time around it. If you roll a marble nearby, it doesn't travel in a straight line. Instead, it follows the curve made by the dip. This is similar to how light bends as it passes near a star, a phenomenon known as gravitational lensing. But now imagine there's a hidden world beneath the trampoline. A mysterious realm physicists call the bulk, which could contain extra dimensions beyond the ones we know. Most things, like marbles and bowling balls, are stuck to the surface, unable to move into this hidden space. But gravity, being unique, might not be so confined. What if gravity's influence can actually extend into the bulk, leaking out from our universe and then echoing back, subtly affecting everything we observe? This idea could help explain a long-standing mystery: why gravity seems so much weaker than the other fundamental forces, like electromagnetism or the strong nuclear force. The Webb telescope recently observed a cosmic effect, light bending more than scientists expected, almost as if gravity was acting stronger in certain regions of space. Meanwhile, in a quantum physics lab, researchers noticed a microscopic effect. A tiny bit of energy seemed to vanish and then reappear, as if it briefly dipped into that hidden dimension before returning. It's as if one team saw only the shadow, while the other glimpsed the actual object casting it. Two perspectives on the same mysterious phenomenon. Both teams, working at opposite ends of the scientific spectrum, caught a glimpse of the same hidden dimension, one from the vastness of the cosmos, the other from the tiniest scales of quantum reality. This is the extraordinary place where quantum discoveries and cosmic observations meet, hinting at a deeper connection in the universe. The evidence may be subtle and easy to overlook, but the implications for our understanding of reality are truly enormous, opening doors to new realms of science. The claim sent shockwaves through science. Theorists who rely on extra dimensions for string theory and M theory saw hope for vindication. The energy signature from the quantum leak and the gravitational anomaly from Webb are mathematically congruent. Too specific to be coincidence, some argue. It's like finding a unique key that unlocks two different doors. But skepticism is strong. Extraordinary claims need extraordinary evidence. Both experiments are on the cutting edge, where errors are common. The quantum leak could be noise, the Webb anomaly, a miscalculation or unknown matter. Correlation doesn't mean causation. Science is full of coincidences that led nowhere. Before rewriting textbooks, every mundane explanation must be ruled out. The debate isn't about belief, it's about evidence. Why search for extra dimensions? It's not just curiosity, it's about solving deep problems in physics. Gravity is incredibly weak compared to other forces. A fridge magnet can lift a paperclip against Earth's gravity. Maybe gravity isn't weak. Maybe it spreads into extra dimensions, diluting its strength in ours. This could solve the hierarchy problem, another motivation unifying physics. General relativity and quantum mechanics don't work together. Theories like string theory require more dimensions, 10 or 11, for the math to work. In string theory, everything is made of tiny vibrating strings, and their vibrations create all particles and forces. But the theory only works if extra dimensions exist. For decades, this was just math. Now we might have the first real hint. Finding an extra dimension could be the Rosetta Stone for physics. If this discovery holds up, it would revolutionize our understanding of reality. our universe would be just a slice of a much larger, multidimensional structure. It could solve mysteries like dark matter. Maybe it's ordinary matter on a parallel brane, invisible but gravitationally connected. Dark energy, the force accelerating the universe's expansion, might arise from the geometry of hidden dimensions. Studying these dimensions could reveal the engine driving cosmic acceleration. Beyond cosmology, new technologies could emerge. If we learn to manipulate extra dimensions, who knows what's possible? Every leap in technology began with a fundamental discovery. This could be the first page of a new chapter. The implications stretch from the fate of the universe to the future of human innovation. The adventure is just beginning. Excitement is high, but science demands patience and rigor. Replication is the first step. Other teams must find the same signals using different tools and data. If the effect is real, it should appear again and again. Independent verification is science's immune system. Next, new experiments will be designed to test the hypothesis directly. Quantum labs will try to induce and measure the dimensional leak with greater precision. Astronomers will search for more examples of anomalous gravitational lensing. Theoretical physicists will build models that make new, testable predictions. If future experiments confirm these predictions, the case grows stronger. Data informs theory, theory guides new experiments. A feedback loop. The scientific community demands converging evidence from many sources. This process could take years, even decades. The bar is high, as it should be for an idea that could reshape everything. Imagine the skeptics are proven wrong and extra dimensions become accepted fact. Our map of reality would expand dramatically, like mariners discovering a vast new ocean. The next quest: explore the properties of this new dimension. How big is it? Is it empty or full of its own structures? We'd build new sensors and experiments to peer into this hidden realm. Could information or energy pass through the bulk? Could we harness these dimensions for technology? History shows that fundamental discoveries lead to unimaginable applications. We stand at the edge of a new reality, asking, what else is out there, just beyond our senses? The journey will be long, but the possibilities are as vast as the cosmos itself.